Today I have something rather unique, and it's not a Python tutorial video. I've been a little bit busy with exams the past few weeks, so unfortunately I didn't have time to make one this week, but what I can instead offer is a presentation I gave in a course on the simulation of PET imaging. I plan to dig into some of the Python code I wrote for the simulation in the future, so if you enjoy this video, please be sure to like and subscribe. Well, good morning everybody, and hello YouTube as well. Today I'm going to be there we go. So today I'm going to talk about a little PET Monte Carlo simulation that I did for the Physics 541 course that I'm taking. I should warn you that there's nothing super novel here, but I think it's a good review of what PET imaging is. And of course, in 3 dimensions, PET imaging is very complicated to sort of wrap your head around, but especially in 2D, I think with something like this, it really helps sort of understand what's going on in PET. So as informative as it was for me to actually go through the simulation, I think it will be fantastic to hear and sort of remind yourself about various things that go on in PET. So as very basic review, PET stands for positron emission tomography. I'm sure we all know this. Positron, of course, is the antimatter counterpart of the electron. Emission is the production or discharge of something, and tomography is imaging by sections or sectioning. So these 3 words come together. You know, there's something to do with a positron, there's something to do with emission, and there's something to do with creating an overall image that's going to be used for something helpful for diagnostic purposes by, sections or sectioning. And so the physical mechanism of PET, which contains all 3 words, is, something we work a lot with is fluorine 18. We usually attach it to a radiopharmaceutical that binds to certain areas in the body. But what happens is that you have a proton turning into a neutron, and to conserve charge, you have a positron emitted by the nucleus. So that's sort of step 1 in PET. So you have this material emitting positrons, and the next step is that, matter is full of electrons in your body. There's lots of electrons everywhere. So the positron will annihilate with an electron. This is a known process, and 2 photons will be emitted back to back. And the reason they're emitted back to back is for conservation of momentum. Of course, that's assuming that the positron and electron are moving slow. Of course, they're only truly emitted back to back in the rest frame of the positron and electron, because then you have no momentum back to back, and the net momentum is 0 as well. So I want to give a really easy example of PET detection for a point source, and I think this sort of helps understand the process that's going on. And it's really easy to do PET detection for a point source, but when you have a continuous volume, that's where things get complicated. So imagine you have a point source at this little red dot that I show here, and you know that photons are emitted at 180 degrees back to back in the rest frame of the electron and positron. So you can assume for now that the rest frame is basically the same rest frame as the detector rest frame. And so you can look for pairs of detected photons during data collection. So I have a detector here, and say a point source emits 2 photons back to back. And you know that the point source is somewhere along that red line here. If it was detection here, that's assuming no time of flight. Of course, we now have PET scanners that are more advanced, but assuming that you can't tell the time difference between these 2 stars, all you know is that the point source is somewhere along this line. But if you have one more detection event, for example, like right here, all you have to do is look at the place where these lines intersect each other, and you know exactly where that point source is. So a point source for PET detection is very simple. But it gets complicated in reality, where you don't have a point source of things being emitted. You have a continuous distribution of radionuclide. And so maybe you have a detection event here, an emission here for 2 photons, emission here. Of course, these lines are intersecting, but the emission didn't happen here. It happened here and here. So it becomes more complicated. And what you need is a significant use of statistics to get the best estimate. So you have millions and millions of these events, and you ask yourself, what's the most likely way that this decayed to get an actual image? And I'll get into that in a little bit. It's a little bit complicated now. And so I want to go over a few detection issues that happen in PET. Up to now, I've been saying that the two photons decay back to back 180 degrees and that the rest frames are equal. But of course, I made a few assumptions, and there's a few things in PET that you have a few issues with. So everything was an ideal situation. One thing that happens is that the positron that's emitted from the decay travels a finite distance before the photon emission, right? So you have a decay event here, then you have electron-positron annihilation, and then maybe the event is along this line here. Of course, the decay is over here. And this is about the order of 1 millimeter here. So I've exaggerated everything on this slide. The other thing that happens is that the rest frame of the positron and electron is not the same rest frame as the scanner, because of course the positron is carrying momentum as it collides into the electron. So what happens is that the emission of the photons is not exactly at 180 degrees. So you have lines that are sort of bent like this. Of course, this is a huge exaggeration in reality, but this is something that happens. The final issue, and this is the one that I'm going to deal with in this presentation, is attenuation. So there's a non-negligible probability that the photon will actually be attenuated in matter. And I have these purple lines here, and the blue, I guess, is supposed to represent matter. And so the probability that these photons, both photons, are detected is equal to this expression here. It's e to the negative, and you integrate over mu, which is the attenuation coefficient, over all space in this blue here. So I would just integrate over this entire purple line, and that's the probability that the thing actually gets detected. And so if mu is equal to 0 everywhere, there's no attenuation, substitute that in this integral, the probability of it being detected is 1. If mu is really high, you have that exponential decay, and the probability of it being detected sort of approaches 0. So you can see the intuition behind this formula here, at least like that. And so what happens is that places where these photons are emitted in high attenuation regions of the body, they get detected less than regions of the body where there's less attenuation. Less attenuation, you get more detected events, and I'll get into that in a little bit. And so, of course, all these effects accumulated together, what happens is that you might, if you're lucky, if the photons don't get attenuated, you might arrive at the conclusion that the decay happened somewhere along this red line. That's if the photons aren't attenuated. And as you can see, this red line is nowhere near the decay. Now, this is sort of a huge exaggeration of reality. Of course, this red line is a lot closer to this red dot, but you can see that these effects sort of become cumulative, and you have to correct for these various things. And the only thing I'm going to deal with in this presentation is attenuation correction. So the fact that in some regions of the body, you have proportionally more photons detected because there's less attenuation going on. And so for an example here, like say I have a decay here, there would be more attenuation through this region. It's darker, for example, and less attenuation through this region. And then maybe this is really attenuation. So if you had decays happening in this dark blue region, maybe a lot of these get detected, whereas events down here in this sort of region, maybe they get detected more often. And so you have to adjust for this when you want the true concentration of radiopharmaceutical in the body. And so before I get into sort of the mathematics of my simulation, I want to just go over a few things. And I'm going to define lambda of xy. This is the radionuclide concentration in 2 dimensions. So everything here is in 2 dimensions. Don't worry about a 3D body. It's a very simple simulation. So there's the radionuclide concentration, xy, and there's something known as the synogram, and it's sort of a function of r and theta. And so this is a different way to represent the radionuclide concentration. And you might wonder, like, why do we care about the synogram P of r theta? Well, it turns out when you actually collect data using a scanner, the raw format of that data is P of r theta. And what we want to know is how do we go from P of r theta to lambda of xy? So the number of detected events is, we want to represent it as a function of r and theta, because that's how we measure it in the scanner. And then we want to be able to take that and turn it back into lambda of xy, which we can then use for diagnostic purposes. So suppose I have this concentration here, lambda of xy. Maybe I have more radionuclide concentration in the yellow region, and then this black thing is the detector. And I plot the number of counts versus r, and r is just the position along the detector. And maybe I get more counts in the middle like this, so that's at theta equals 0 for the detector. And then maybe I rotate the detector 45 degrees, like this, and then I get a different distribution of number of counts versus r. So this is a totally different distribution here. It's the same lambda here. and I can do this for a bunch of different values of theta. So now I have two parameters. I have theta and r, and I have the number of counts at each value of theta and r. And then I can construct what's known as the synogram like this. So I have theta on one axis, r on another axis, and then this height here, the number of counts in the middle like this. So this doesn't correspond to this distribution, but that's sort of what happens. Now, the synogram, like I said, is what you actually measure with the detector because you know the detector angle and you know where along the detector you take the counts. So what we want to do is we want to say, how do we take this synogram and reconstruct lambda? And it's not a one-to-one perfect operation. If you have infinite values of theta, technically it is, but of course you only have finite detector scanner angles, so it's not, you can't perfectly reconstruct lambda from the synogram. So you have your raw data and you want to know what's the real distribution of the radionuclide in space. And so there's an algorithm that we use for this. And so there are various algorithms that we can look at, which I'm going to look at in this talk. And so this is the simulation that sort of I went through. So I have CT phantoms. They give the attenuation coefficient everywhere in space. So darker means more attenuation. And I just sort of came up with these by myself in a photo editing software. I wanted to see if there were any significant differences between phantoms. And then I also came up with a radiopharmaceutical distribution, so that this is sort of representative of organs or tumors. So I have the tumor locations here in black, and then the tracer concentration, lambda of xy, that's represented by the color. And to make it a little bit more variety here, I have it so that there's more activity in the center of the tumors. So it's really bright in the center, and it sort of decays going out. And so the simulation, you have to be very careful about what you're talking about here. So each pixel of this represents decays, and its lambda is the mean of a Poisson distribution. Because when you actually collect data, of course, you're drawing a random number from this. Decays are stochastic in nature. So each pixel is a Poisson random variable with mean lambda of xy. So when you actually collect decays in your scanner, you have to draw a Poisson random variable for each pixel, and you get n of xy, which is here, and it doesn't look like lambda. And of course, you see that I have more than 500 here, even though 500 was the max in lambda, and that's because I'm drawing Poisson random variables. So I get something like this. For each of all of these decays, so the total number of decays is the sum of n of xy, I get a random uniform decay angle theta. So each one of these points on this histogram, this 2D histogram, there's a decay angle theta. And so what's happening in the phantom corresponds to the same region here. And so you get a line that looks like this. You do this for each decay, and you compute the probability of no attenuation by integrating over this phantom, this integral here. And you get the detected decay. So this is what you actually measure in your detector. And so what you can see in these two circles, I don't know if it appears very well on the screen, but I have this brighter region here and a sort of darker region here. So depending on the phantom and the region of like where things are getting attenuated, I have bright spots and dark spots. And this dark spot, of course, is right in the middle of this dark triangle. So I have to adjust for this in the end because I know that really it should be kind of the same everywhere, but here I'm showing some regions are brighter and some regions are darker. So then what I do is oh, by the way, I want to make a point here. When I say D, capital D, that means what you actually detect. And N is what actually happens. So N is like before attenuation, and D, detected, means after attenuation. So what I do is I use my detected decays with the D here to compute the synogram. And I can do this since X, Y, and theta are known for every single decay. So I can compute R along the detector, and then I can get this detected synogram. So everything now is a simulation to get this detected synogram, and this is what you actually measure when you're collecting data in like a clinical setting, for example. Of course, this is 2D. People aren't 2D. So the next step is now that we have this, we want to test various reconstruction algorithms that are used in clinical practice. So I'm going to use, the first step is I'm going to use an algorithm from the TomoPy Python package. I suggest checking it out. It's pretty cool, to get an estimate for the number of detected decays. But of course, the detected decays aren't the same as what actually happened. So then I have to use attenuation correction to get an estimate for lambda. And the whole process is sort of represented here, and I'll get into these predictions here. But what you can see is that different algorithms give different results here. And some algorithms have these sort of artifacts that extend throughout, and some are sort of localized, but again, I'll talk about this a bit later. And so the first thing, actually, before I get into these various algorithms, is I want to talk about attenuation correction, because this is sort of the main thing I was looking at. So given an estimate of the detected decays everywhere in space, you can get an estimate for the true number of decays by dividing by the probability of detection for that pixel. So n is equal to nd over p. So if p is really small in some region, then this thing on the right becomes big, and so n becomes increased. So if you know that a particular region has a small probability of detection, you want that to be weighted higher. And so that's what this p does. Whereas if p is equal to 1, if you know it's going to be detected, then the number of detections is equal to n here. So that's sort of the rationale behind this equation. And the question is, how do you get p of xy? Because you know nd, you just need p. And so p is obtained by averaging the probability of detection of decays equally spaced in theta. So I pick a point, xy, right? And then I look at all these integrals along all these various lines, and I take the average, and that's what's expressed here. So this 1 over n, sum I equals 1 to n, well, this is just an average that shows up all the time. And I'm averaging over all these probabilities here. And si of xy, that sort of represents one of these red lines. So I average over all possible decays that can happen at a certain point, and that's like the probability that decay at that point is detected. And so then I can adjust to get n afterwards. And so what I do is I use an algorithm, I get the estimate for the number of detected decays, and then I adjust using attenuation correction to get the true number of decays. And then what I can do is I can look at algorithm convergence for, like, I think I used 1, 2, 3, 4, about 10 different algorithms here from the TomoPy Python package. And there's only, like, obviously I can go into depth in these algorithms, and they're quite complicated. But a few things to note here is that the best one is I believe it's called total variation. And so that one performed the best for all these phantoms here. So that was the lowest. The maximum likelihood variations were actually performed really bad. So you can see that these algorithms, by the way, I show a number of iterations here. That's because the way it works is you, to get the best result, you have to do a process over and over and over again on the image until you eventually get the best result. It's the same thing sort of like with machine learning, how you train it over many iterations and then you get a final result. And so this is the convergence of the algorithms. The maximum likelihood one, actually, it reaches a minimum point and then it gets worse with more iterations. So these are like the basic reconstruction algorithms that you're sort of taught at first. And so you can see that these variations of maximum likelihood, the ones below actually do better. So obviously over time people realized, well, the basic ones aren't doing great, so we need to come up with variations of them. And for all different 4 phantoms, and you can see that, so each color represents a different one of those 4 phantoms I showed. And there's a little bit of variation between phantoms. You can see that, for example, phantom 4 performs the worst for here, but for the maximum likelihood ones, you can see that it's not actually performing the worst. It's the green and orange. So that's a little bit interesting. There's some artifacts of the algorithms. So all the maximum likelihood estimators, so all of these ones with the black sort of on the outside here, these are variations of maximum likelihood. And you can see that they don't have artifacts that extend throughout the image. And of course that's good, because if you have a tumor that's localized somewhere in the body, you don't want things propagating outward because it might, interfere with other things. And whereas the other algorithms, I said that total variation performed the best. And by the way, it performed the best inside the tumor. But when you consider stuff outside the tumor, well, maybe it's not the best because it's actually propagating stuff outwards here, and that could interfere with other predictions. Then finally, and I'll go over this really quick, there's something known as, yes? 3 minutes, okay. I think we have time here. So partial volume correction, this is something that's occasionally used in PET. And so the predicted concentration, so here's like a really small region. This sort of represents a tumor. This is the true lambda, which I know because I'm doing a simulation, and the predicted lambda. And the predicted lambda, there's leakage outside the tumor. And the question you ask is, well, suppose you have knowledge of the shape of the tumor through, for example, MRI, where you have really high resolution idea of what the tumor looks like. How do you adjust this prediction if you know the shape of the tumor to get this here? That's partial volume correction. It's one type of partial volume correction. So I used an algorithm from a paper here. There's a link. I'll upload the slides. Requires the use of MRI information. So what I did is I used the tumor locations here as the MRI image. It's either 1 or 0. So it's a way of representing the tumors here, the tumors not here. I found an error in the paper, actually, when I was going through it. You have to minimize a loss function. I don't want to go into the math here, but you need the analytical gradient for the way that you minimize it. So you take the derivative of this with respect to O. O is a pixel of the image. And they forgot to use the chain rule here, so I found another term, and then it actually worked even better after using this. So again, I don't want to go into this too much. And so what I did is I experimented with a few parameter configurations. There's a lot of adjustable parameters when you do partial volume correction. And so the black dotted line is the true concentration here. The blue is the estimate, and then the red is the partial volume correction. And I didn't get great results because I was a little bit rushed, and I wish I could spend more time on this. But the main result here is that the partial volume correction image matches the boundaries a little bit more. The red sort of goes abruptly up like that. And what you want to do is you want to remove the leakage, but of course there's still leakage, in some of these images here, even though this boundary is sort of matched like that. And the one interesting thing is you can see on this bottom right image, there's a black line here that represents a known small tumor. The blue missed out on it, but the partial volume correction was actually able to get it. So this suggests that in some cases, the partial volume correction can be used to get the true concentration, even though it might be missed in normal, using just the algorithms that I talked about before with no partial volume correction. So in conclusion, the PET Monte Carlo simulation, I believe, was successful. I learned a lot doing it. Attenuation was simulated properly. I learned about Synograms and raw PET data. There were various reconstruction algorithms tested. Unfortunately, I couldn't go too much into depth in them here, but there's a lot of ones used in practice, and they have to pick the best ones, of course, in the clinic. Some perform better than others in terms of the RMSE inside the tumor, the concentration, and some perform better than others with regards to artifacts that extend throughout. And finally, I tested partial volume correction. I found an error in the paper. I emailed the authors. They haven't got back to me yet. I assume they're busy. It was an old paper. Maybe they don't even know it exists anymore. I briefly tested the parameter configuration. I wish I could spend more time on that. So I wasn't able to explore it further and get even better results. So anyways, that's it.